sodium amide I told you that it is non-terminal or internal. The non-terminal or internal alkyne is converted into a terminal alkyne, right? Going to give you mechanism also. Let me first give you an example. So this is butadiene. No doubt it's internal or non-terminal, right? See, with sodium amide, yeah, this step is very interesting. You will understand this only after the mechanism. This is what you get. Then on adding water, I mean on adding acid, on acidification, we get this terminal alkyne, right? Let me give you mechanism for this. Okay, we'll see how butadiene is converted into this. See, there is a change in position of triple bond. You must have observed. Let's see the mechanism of this. Now, initially, let us take out a hydrogen, right? Using the base NH2 minus, you can abstract this, then it of course becomes minus, I mean this comes here, right? Then it will be this CH2 minus, right? Now again, in the next step, because this negative charge and the pi bonds are in conjugation, it can be taken this way. Right? Then we'll be getting CH3, C, it gets a negative charge, a double bond C, then again a double bond CH2. No, this minus is gone. Okay. Now here, let me consider ammonia. We have sodium in liquid ammonia, right? This minus takes away H plus, and this again becomes NH2 minus. Let us write it minus NH2 minus. Okay, then this will be CH3, then of course a CH double bond C double bond CH. What alene type of structure? This on further treatment with another molecule of base. Okay. in this case, it again abstracts another H plus. Let us take a hydrogen out. Come on. Now this and H2 minus abstracts H plus. Okay. Then CH3, CH, double bond C, this, and then CH minus. That's it. We are almost there. This one comes here. This goes towards the carbon. It's a simple thing. Then finally, we get this CH3, CH minus. Okay. It is this. Now give it a H plus. Take ammonia again. Now this one. So minus NH2 minus. Finally, you get CH3, CH2, C triple bond, CH. See the thing what you have started with and what you have ended up with. This is non-terminal. This one is terminal. Isn't it? Right. Now, let me also tell you one more interesting thing. So in this case, we have used, say, two equivalents of or two molecules of sodium amide. Let me give you one more interesting. Now look at this example. Now suppose this is considered right. See with sodium amide, two equivalents. What do we get? Yeah, we get this. Okay. Whereas when sodium, of course, this finally gets converted into, I mean, when these two chlorines go along with this, of course, we get a terminal one. But if the same sodium amide is taken in excess, this will finally get converted into a terminal one. That is okay. But if sodium amide is taken in excess, then it will be CH3, CH2, C minus, then Na. This is what we get. In fact, we generally go with this when sodium amide is considered. Okay. Then let us see the next variety, that is alcoholic KOH. See with alcoholic KOH, yes, we know that the terminal alkynes are converted into non-terminal or internal alkynes. Let me give you an example with mechanism even for this also. Consider but1-ine. This is terminal alkyne. See, with alcoholic KOH, we get but2-ine. Okay. Let me give you the mechanism. Then this will be clear. Again, the same kind of abstraction of protons and rearrangement. Let me show you. See, with OH minus, I mean the base, we can actually abstract this hydrogen. Okay. Now, when that is abstracted, we get CH3, CH minus. C triple bond CH. Right? Again, go for this. A double bond is formed. Even this also becomes a double bond. CH3, CH, double bond C, then this will be CH minus. Now, see, in the first step, we have actually abstracted a proton using a base. Now, that proton will come into picture. It is in general, if you want, you can actually take H3O plus, no problem. But because we are in basic medium, we are considering the same H plus what is been abstracted in the beginning. I mean OH minus and this H plus combined to form water. From that I am taking a H plus. Okay, so H plus, then this will be like CH3, CH, double bond C, then this of course is CH. Okay. Now again repeat the same steps. We'll have to abstract this. Come on. Then we get CH3, C minus, C minus, double bond, then double bond CH. That's it. See, as and when this comes here, we are going to get our terminal alkyne. Now even here also, we have removed the H plus. Now that H plus is what we are going to add. Let us take it here. Now then, CH3, this will be a triple bond, CH2. Oh, we have to actually go for one more step. Let me just do this. CH2, then minus here. Now we have to add the H plus. Correct. Okay. So we'll get the final thing. C triple bond C, then CH. Yes. So this is how we can convert the terminal alkynes into non-terminal using alcoholic KOH. Okay. Next. Another preparation method is dehalogenation. Dehalogenation is nothing but removing the halogen atoms. Look at in general, zinc dust in alcohol is used for a dehalogenation, right? We can also use magnesium ethanol, even sodium iodide acetone, used even in the preparations of alkenes or on heating with silver. Any of these is okay. Now, on dehalogenation, finally, we'll get this. See, along with this, we get 2 moles of ZnH2. So all these are eliminated. Okay. You are eliminating 2 atoms from each carbon atom. So you get a double bond between the two, extra 2 bonds. You get ZnH2 if zinc dust ethanol is used. Otherwise, you get MgH2 or else sodium halide or else silver halide. These are going to be the byproducts depending on what the reagent is. Now, let us take a simple example. No much interesting. Simple elimination of bromine. Using the same reagents, we get butadiene. That's it. Go for ZnBr. Okay. The same way it can be MgBr2 or NABr or even silver bromide. Right? So these are the preparations of alkynes. Now the properties. In the properties, most important one is acidic nature of alkynes. Consider acetylene or else you can consider alk1ines. I mean those which have got a triple bond after, the terminal carbon. Alk1ine, nothing but a terminal alkyne. Now in this case, if you observe, one second. See the hybridization of the carbon atoms of acetylene are that of alk 1 ine. I mean the triple bonded carbons is sp, right? When you consider sp hybridization or sp hybridized carbon, see the sp hybridization will have 50% s character, right? Consider sp with 50% s character, sp2 with 33.33% s character, then sp3 with 25% s character, right? Now if a bond has more s character, I mean as s electrons are much closer to the nucleus, it will have more electronegativity. 50% s character. So as s electrons are much closer to the nucleus, okay, because of this, the nucleus will have more electronegativity. More electronegative in the sense it will have more tendency to attract the bonded pair. Towards the nucleus. I mean towards carbon nucleus. Look at this. See the bonded pair that is lying between carbon and hydrogen is abstracted, I mean is attracted towards carbon. So now these hydrogens can easily be replaced. Okay. So such hydrogens are said to be acidic or active hydrogens, right? So these are acidic or active hydrogens. This, those attached to sp carbons are acidic or active, can easily be replaced. Okay. So in general, if we observe this, you know, the electronegativity order follows this particular order: sp, sp2, sp3, and then the acidic nature order. Okay, that will be like again sp, sp2, sp, because greater the electronegativity, greater is a tendency to attract the bonded pair. So are the hydrogens easily replaced. Therefore, the hydrogens are acidic. Now, let us see some reactions due to acidic hydrogen. So, using a metal, acidic hydrogens can, of course, be replaced. Let us consider sodium in liquid ammonia. In the presence of a catalyst iron plus 3. Sodium reacts with ammonia to form sodium amide or sodamide. Okay. One of the hydrogens is removed, eliminated. Now this sodium amide with the acidic hydrogen. See what happens. Okay. RC triple bond C minus. But anyway, you got Na plus. See, this is called sodium alkynide. Started with an alkyne. So this is said to be sodium alkynide. Anyway, ammonia is eliminated. Now this is your acidic hydrogen. Okay. Now interesting thing is this sodium alkynide is actually used for the preparation of higher alkynes. Now when this is treated further with an alkyl halide with a different alkyl group, depending on the number of carbon atoms that you require in the higher alkyne, you can actually consider an alkyl halide here. Now the C minus attacks, the X minus goes up. Okay, so that is how we get a higher alkyne. I'll give you an example. R C triple bond C, then R minus, and the thing eliminated, removed is sodium halide. Now this is how a higher alkyne can be prepared. This is very important. We have a previous IIT question on this. Let me give that. Let us prepare SEDEC 3-ine. Starting with the acetylene. Very interesting. Now, first of all, what is this deck 3I? Triple bond after third carbon. 4 plus, let me write 4 plus 5, 9. Then 1 CH. Right. So, the triple bond is after third carbon. Now, this is the basic structuring of acetylene. Right. Now, these are the things to be used. I mean, these are going to be replacing the acidic hydrogen. Let's see. Starting with acetylene, you can use the sodium or lithium in liquid ammonia, right? Of course, the regular sodium amide. Come on, do this. It will go here. So this is how we get monosodium acetylide. Now to this monosodium acetylide, let us add this part first, or else the other part, this area. Let us add it in this format. CH3, CH2 taken 5 times, then CH2 taken 5 times, it has to be Cl. So let us take it this way. CH2 taken 4 times, CH2 Cl. That's it. Now this minus will attack here. You'll get the required entity. H, C triple bond C, then CH2. Of course, these two is nothing but CH2 taken 5 times, then go for CH, right? Now, on further reaction with another molecule of sodium amide, yes, again, this area. This is what. So, you'll get another